Hi. So far, we have seen the definition of the integral as a limit of Riemann sums. Using this definition, we always have a way to determine an integral approximately. Replace it by a Riemann sum. Indeed, we can always subdivide the interval of integration, choose sample points, and calculate the corresponding Riemann sum. In fact, this principle provides a basis for numerical integration. But it will almost never produce the exact value of the integral. Moreover, it can be very tedious to actually evaluate the Riemann sum. Luckily, there is an extremely powerful tool to evaluate integrals exactly. It is called the fundamental theorem of calculus. You have probably seen it in high school. Let me recall the precise statement. Suppose we have the following: a continuous function f defined on the interval from a to b, and a function capital F such that small f is the derivative of capital F. Then the following holds. The integral from a to b of fx dx is equal to capital F of b minus capital F of a. Any function with derivative equal to small f is called a primitive function or antiderivative of small f. Those terms can be used interchangeably. So by this theorem, integration comes down to finding a primitive function f and evaluating fb minus fa. Let me show you an application of this theorem in an example. Let us consider the integral from 1 to 2 of x squared dx. We need to find a primitive function of the square of x. That is, find a function which has x squared as derivative. Note that the following function will do. Capital F of x equal to 1/3 times x cubed. To check that this is indeed a primitive function, we calculate the derivative. F prime of x equals 1/3, and then we use the power law, times 3 times x squared. The prefactors cancel, and we are left with x squared, which is indeed our original function. The fundamental theorem of calculus tells us that the integral is equal to capital F evaluated at the upper boundary minus capital F evaluated at the lower boundary. So let me write the integral again. The integral from 1 to 2, x squared dx. And now it is customary to use the following notation. Open with a square bracket, put the primitive function here, 1/3 times x cubed, and then put the boundaries here. This notation means precisely what I just said. Take the function 1/3 times x cubed, evaluate at the upper boundary x equal to 2, evaluate at the lower boundary x equal to 1, and subtract. The advantage of this way of writing is that you can make clear what primitive function you use before you evaluate. It makes the calculation more transparent, and I advise you to do the same when you write down your own calculation. So this is equal to 1/3 times 2 cubed minus 1/3 times 1 cubed. Of course, we can simplify this. This is equal to 1/3 times 8 minus 1/3 times 1, which is equal to 7/3. And this is the final answer. This is the exact value of this integral. And it is also the exact value of this yellow region in the picture. It is approximately equal to 2.33. Let me correct that. 2.33. So the area of this yellow region is approximately equal to 2.33, which seems reasonable if you look at the picture. But what's important is that we calculated the integral exactly. If you think of it, the fundamental theorem may seem a bit strange. Roughly, it tells you that integration and differentiation are inverse operations. But if you compare the definition of differentiation to that of integration, it's really not clear at all that these are related. In a separate video, I will give an explanation why this theorem is nevertheless true. I would like to end with some remarks about primitive functions. First of all, primitive functions are never unique. Look at the example. We had a function capital F equal to 1 over 3 times x cubed, and a function small f equal to x squared. Small f is the derivative of capital F, so capital F is a primitive function for small f. But we can add any constant to capital F, for example 10. Let's call this new function capital G. The constant disappears after differentiation, so the derivative of capital G is again small f. So capital G is another primitive function of f. This works in general. If you have a primitive function, you can always add a constant to get another primitive function. In fact, this also works the other way around. If you have two primitive functions, capital F and capital G, of small f, then they must differ by a constant on the interval of integration. To see this, note that both capital F and capital G have small f as derivative. So the derivative of capital F minus capital G must be 0. This can only happen if f minus g is constant on the interval of integration. The important conclusion is that you have one primitive function, capital F, of small f. You can find all others by simply adding an arbitrary constant. The set of all primitive functions is often denoted by an integral without boundaries, integral of fx dx. We call this an indefinite integral. For example, the integral x squared dx denotes the set of all primitive functions of x squared. To make this set explicit, we write one primitive function, for example, 1/3 times x to the x cubed, plus c to indicate all the others. Don't forget the plus c, otherwise you only have one primitive function. In the exercises after this video, you can practice with the fundamental theorem and the concept of primitive functions. In the following video, I will show you why the fundamental theorem is true.